Welcome everyone. I am Dr. Soumyajit Ghosh, and in this lecture I am going to talk about the conducting polymer, which is a topic of chemistry course 21 CYB 101J. So conducting polymer is a special type of polymer which exhibits conductivity. I'm going to talk about that how it is different from the conventional polymers and how the conductivity is originated in the conducting polymer. Then I'm going to discuss about the different types of conducting polymer, intrinsically conducting polymer and extrinsically conducting polymer, and also how the conductivity can be enhanced by p-doping and n-doping, etc., and their mechanism. Lastly, I'll talk about some of the examples of conducting polymer such as polyacetylene, poly-3-hexylthiophene, their properties, their synthesis, properties and applications, etc. So, before we discuss about the conducting polymers, we should know that what is the general property of the polymers. Usually the polymers are not showing any electrical conductivity. Usually the polymers are organic compounds made up of carbon, hydrogen, nitrogen, etc. and have covalent bonds. And because of these covalent bonds, they are not supposed to be electrically conducting because there is no availability of free electron. In this regard, that conducting polymers comes under the special category because it can conduct electricity, and this conductivity is originated to the available free electron. So usually generally polymers that are used in daily basis are insulators, but the conducting polymers conduct electricity through this available free electron. The Nobel Prize in Chemistry 2000 was awarded jointly by Alan Heger, McDermid and Hideki Shirakawa for the discovery and development of conducting polymers. And these materials, based on doped polyacetylene and other conjugated polymers, they are sometimes referred as synthetic metals. So if we want to see the conducting polymer, that structurally why it is different from the other type of polymer, we'll see that conducting polymer comprising of conjugated carbon chain consisting of alternating single and double bonds, where the highly delocalized, polarized and electron dense pi bonds are responsible. So basically it poses the extended conjugation of available p orbitals containing electrons, and this is responsible for this electrical behavior. So typical conducting polymers include polyacetylene, polyaniline, polypyrrole, polythiophene, polyparaphenylene, polyphenylene, vinylene, etc. So what are the applications of conducting polymers? Why it is so important? These have a wide array of applications, including the lightweight rechargeable batteries for portable devices and vehicles. It would serve both current carrying and ion conduction functions by replacing traditional electrode and electrolyte substances. Conducting polymers are also used in building circuitry elements, both passive conducting circuits and active PN and Schottky junctions. Other potential applications include transparent anti-static coatings for metals and electronic devices, light emitting diodes, electrodes, biosensors, transistors, etc. So, what are the properties of conducting polymers? As we know that conducting polymers have high extended conjugation of available p orbitals containing electrons, and that accounts for the delocalization. And due to this delocalization, it is having this exceptional conductivity. The conducting polymers have high melting and softening points because of the mobility of the repeat units is highly restricted due to the presence of a fully aromatic ring structure and the absence of free rotating groups. Number two, the conducting polymers show excellent chemical, thermal and oxidative stability due to low hydrogen content and aromatic structure, because there is a conjugation is there, so it has a restriction on free mobility, and therefore it is having the excellent chemical, thermal and oxidative stability, and also they can be processed into a highly ordered crystalline thin film that is electrically conducting upon doping, and moreover they are insoluble in many common solvents, etc. Next, we are going to talk about the types of conducting polymer. As we know that conducting polymer is basically the linear backbone chain with extended conjugation, and the electrical conductivity is attributed to the delocalization of the pi electron over this backbone chain. So the different conducting polymers are classified according to their composition. This table presents some of the organic conducting polymers according to their composition. Mainly, broadly, the conducting polymers can be classified into two categories. One is intrinsically conducting polymer and another is extrinsically conducting polymer. Intrinsically conducting polymers are having the electrical conductivity which is very inherent in nature. So and one is it has again the subcategory, the conjugated conducting polymers like polyacetylene, etc. So these are having the electrical conductivity due to the extended conjugation and the delocalization of pi electron. And another category is the doped conducting polymers. So by adding some foreign agents, the conductivity can be enhanced. And extrinsically conducting polymers, that means when the polymers can be blended with some conducting elements or conducting planes, it will exhibit the conductivity. So initially it doesn't have any conductivity, but whenever it will be mixed or blended with some conducting element, it will show the conductivity. So these are extrinsically conducting polymers. So the conducting polymers again can be classified based on the composition. We all know that it comprises of main chain. So without heteroatom or with heteroatom, the conducting polymer can be segregated or classified. If the polymer backbone does not contain any heteroatom, and again in that category, if the building block, the monomeric unit is the aromatic cycle, then this is one type of conducting polymer. The examples are polyparaphenylines, polynaphthalines, polyfluorines, etc. And without aromatic cycle, only if the double bonds are present, then polyacetylene. If the conducting polymers contain heteroatom, and that also it can be nitrogen or sulfur. If the nitrogen is part of the aromatic cycle, then the examples are polypyrols, polyindols, etc. And if the nitrogen is outside the aromatic cycle, the example is polyanilines. If the sulfur is in the aromatic cycle, then the example is polythiophene. That means in the building block, building monomer unit contains the thiophene, and that thiophene, the sulfur, is part of the aromatic cycle. And if the sulfur is outside the aromatic cycle, the example is the polyparaphenylene sulfide. So this is how we can see that without heteroatom or with heteroatom also the conducting polymers can be classified. So now we'll move to the polyacetylene conduction through conjugated pi system. So we'll try to understand the underlying phenomena of electrical conductivity in the conducting polymer. As we know that it consists of the polymer backbone chain with extended conjugation, and this carbon has the sp2 hybridization and it has a available p orbital. So if we see that this is the carbon backbone chain and these p orbitals are orthogonally oriented, and this contains an electron, and each p orbital contains one electron, and these electrons undergoes delocalization. Because of this delocalization in this backbone chain, it leads to the electrical conductivity. So the biggest advantage of conducting polymer is that gainfully incorporation of flexibility with electrical conductivity. So whatever the conductors are currently present, that cannot be flexible, but the polymers have the added advantage of the flexibility. So flexibility combined with the electrical conductivity, that is the biggest advantage. And these conducting polymers are organic materials. They are not thermoplastic or thermoformable, but of course their electrical conductivity can be fine tailored by changing the substituents. By changing the substituents, the electrical conductivity can be tuned. Now we can discuss few more examples of conducting polymer. In the previous slide, we talked about that how electrical conductivity is originated in polyacetylene, and here we will discuss the polypyrrole. Previously we talked about that conducting polymer with or without heteroatom. So here this is a backbone chain, and this polypyrrole consists of this building block pyrrole moiety, and pyrrole contains the heteroatom nitrogen. So nitrogen is part of this pyrrole moiety, and these pyrrole moieties are connected, leads to the extended conjugation. So here that nitrogen has a lone pair, and this lone pair takes part into the conjugation. Because the nitrogen is part of the aromatic moiety, so the polypyrrole comes under the category where the nitrogen is part of the aromatic moiety, like pyrrole. And polyaniline, the heteroatom nitrogen, is located outside aromatic unit. So if we see that backbone or structure of the polyaniline, there are two parts. One is the benzenoid amine and another part is the quinoid imine. Okay, so this is the part of the benzenoid amine and this is the quinoid amine. So together they form the polyaniline, or we can call it as a pani. So now we'll try to understand that how the electrical conduction takes place in the conducting polymer with the help of the flow chart. For any material there is a valence band and conduction band. For insulators, this energy gap is forbidden. So the electron which is located in the valence band it cannot be promoted to the conduction band. So the valence band to conduction band is prohibited for insulator for this energy gap. While in the doped material, if we add some foreign agents and we can add or we can incorporate some energy level in between the valence band and conduction band, then the electron can be easily promoted to these intermediate levels, and ultimately it can go to the conduction band, and therefore it leads to the electrical conduction and the current flows. So what happens into the doped polymer, that due to this doping agent, the polaron is being created, and ultimately when there is a polaron is extended, and that leads to the polaron localized bands in between the valence band and conduction band, and therefore the electron can be easily goes to this polaron band, and from here it can go to the conduction band, and that leads to the electrical conductivity of the polymers. Now next we'll talk about the intrinsic conducting polymers. Here in this type of polymer, the conduction of electricity is due to the conjugation in the backbone of the polymer. The conjugation can be due to either pi electrons or due to the doped ingredients. Basically, it is the inherent type in nature, and this stems from the extended conjugation. So the intrinsic polymer with conjugation, in this type of polymer, the alternate single bond and double bond is there, or it comes from the heteroatom lone pair, and conduction of electricity takes place due to the delocalization of pi electron, or it can involve the lone pair of heteroatom. So the examples are polyacetylene, polyanilines, polypyroles. So these are the conducting polymers containing the heteroatom moiety, aromatic moiety containing heteroatoms. And another category is the doped conducting polymer. In this type of polymers, we can add some agents or materials from outside, and by addition of this material, the conductivity can be enhanced. Actually, the conductance can be increased by introducing positive charge in the backbone, that means the oxidation or reduction. So that is happening due to the N type of material. So these are called doped conducting polymer. So in the p-doping of conducting polymer, what happens that the polymers are treated with oxidizing agents such as Lewis acid or halogens, etc. And after treating with this Lewis acid or halogen, it can oxidize the polymers, creating positively charged sites in the polymer backbone, and therefore it will act as a good conductor of electricity. So it is called as a p-doping or oxidative doping. So what are the p-dopants? Like iodine, bromine, aluminum chloride, AsF5, ferric chloride, etc. So when these dopants are added, this conducting polymer, this takes up the electron from the polymer backbone, undergoing oxidation, and therefore it leads to the creation of positive charge in the backbone, which conducts electricity. That is called a p-doping. And in case of n-doping, the polymers are treated with the reducing agents such as Lewis base or alkali metals, which reduce the polymers by giving the electrons. So in the backbone, there is a creation of negatively charged sites. And because of this reduction, this creation of negatively charged sites in the polymer backbone can enhance the conductance, and therefore it is called as end-doping or reductive doping. So what are the end-dopants? Sodium, potassium, lithium, naphthalites. These are the end-dopants. So in the previous slide we talked about the intrinsically conducting polymer. Now we will talk about the extrinsically conducting polymer. These conducting polymers, which owe their conductivity due to presence of externally added ingredients in them, are called as a extrinsically conducting polymers. We have seen that intrinsically polymer is showing the conductivity which is very inherent in nature. But in case of extrinsically conducting polymer, we are adding some foreign agent or some materials which can lead up to that conductivity. So it can be of two types: conducting elements filled polymer, CEFP, that means the polymers filled with conducting element, and the another one, the blended conducting polymer. So in the conducting elements filled polymer, the polymer do not have the conductivity. Its role is to bind the conducting elements. For example, the added fibers or added conductors. So those are the conducting elements which possess the conductivity. So that can mix, that can bind with this polymer, and therefore that overall composites will show the conductivity. So that conductivity is coming from this conducting element. For example, if we mix with some polymer with some carbon dust or granule from like metallic fibers, that conductivity stems from this carbon dust or metallic fibers. The overall composite, therefore it will have that conductivity. In extrinsically conducting polymers, when carbon black or some metal oxides or metal fibers are added, the polymer becomes conductive. As I said before, the polymer is not conducting, but when it is mixed with conducting elements such as metal oxide or fibers, it becomes conductive in nature. So the minimum concentration of conducting filler required to start the conduction is called percolation threshold. The filler, that means the ingredients that percolate, have more surface area, more porosity and filamentous nature, due to which they can enhance conducting properties. Important characteristics of these polymers are they possess good bulk conductivity, they are cheaper, they are light in weight, they are mechanically durable and strong, they are easily processable in different forms, shapes and sizes. And another one is the blended conducting polymer. Blended conducting polymers. This type of polymers are obtained by blending a conventional polymer with a conducting polymer, either physically or chemically. These blend of polymers conduct electricity. So the two polymers are there. One polymer is conducting in nature, the another polymer can be the conventional type in nature. By blending together either chemical or physically, it will referred as a blended conducting polymer. Such polymers can be easily processed and can have better physical, chemical and mechanical properties. Now we will talk about the electrical conductivity of some common conducting polymer through this flowchart. So we will try to understand that what is the range of electrical conductivity of some of the conducting polymers. So the unit of electrical conductivity is Siemens centimeter inverse. If you see in the left hand side, it shows the range of electrical conductivity of some conductors and semiconductors. So the conductors have the electrical conductivity of 10 square to 10 to the power 6 Siemens centimeter inverse, and that includes copper, iron, mercury. If it is the semiconductor, so this is the range, and we all know that silicon is semiconductor. So this is the range of electrical conductivity, or any material whose electrical conductivity is below 10 to the power 10 minus 10. These are referred as insulators, like nylon, polyethylene, polystyrene. These are the conventional polymers which do not have extended conjugation, absence of delocalized pi electrons. So these do not show the conduction of electricity, and that's why they are referred as insulators. So this right hand side, these are the range of conducting polymers having the range, showing the range of electrical conductivity. So for example, polyacetylene, we all know that it is an intrinsic conducting polymer, but by addition of p dopants or n dopants, the electrical conductivity can be enhanced, and even it will be similar to some conductor material. So by tailoring the substituent, the electrical conductivity can be enhanced. So in the last segment of our lecture, we'll talk about the applications of conducting polymer. As we know that conducting polymer gainfully combines the flexibility with electrical conductivity. So by taking advantage of both these two properties, it can exhibit wide array of applications. The conducting polymers can be used in the manufacturing of chemical sensors, electromagnetic shielding, anti-static coatings, corrosion inhibitors, etc. They are also used in compact electronic devices such as polymer-based transition, light-emitting diodes and lasers, etc. They can be used in organic photovoltaic cell like poly 3XL thiophene can be blended with some N type of material and can exhibit very good photovoltaic efficiency, and also they can be used for microwave absorbent coating, particularly radar absorptive coatings or stealth aircraft. They are used in the manufacturing of printed circuit board because it protects the copper from corrosion and prevents its solderability. So this is about this part 1 lecture of conducting polymers. In the part 2 lecture of conducting polymers, we'll discuss about the in-depth mechanism of p-type and n-type uh, phenomena of the conducting polymer. Also, we'll discuss about some of the polymers, their synthesis, property and applications. Thank you all.